watching me online. And myself are Siva Chidambaram, and research scholar at Department of Earthquake Engineering in IIT Roorkee. And my area of research is on earthquake-resistant design, and by using some high-performance material to enhance the inelastic performance of our RC structures. So we are using various high-performance material which are available in India, and we are trying our level best to enhance the inelastic performance under cyclic loading. In Department of Earthquake Engineering, we are conducting numerous research studies to enhance the cyclic performance, which means seismic performance of various structures like buildings, dams, and RC frame structure, as well as our masonry structures too. And my area is specially narrowed down on earthquake resistant design and to enhance the performance of RC structure using different high performance materials. In my case, I'm going to increase the inelastic performance by using different high performance material in different ways. Like as in India, we have a lot of high performance materials. The high performance in the name it can itself defines the performance is better than the conventional one. Now that's the first point. Now the second is we are going to increase the inelastic performance to provide a better and sustainable structure in this earthquake resistant design category. Like what are the materials are available in India? Like in terms of fibers, we can say steel fiber, carbon fiber, glass fiber, polypropylene, polyester. These are the fibers are available in India, and it is available in various form, like in fiber form, in fabric form, as well as in solid form. So when you talk about utilizing these fibers in an effective way, we have to choose appropriate method to enhance the performance in different way. Like if you use high performance materials as fabric, we can wrap to increase the strengthening purpose. And if you want to use those fibers along with concrete, you can increase the performance rather than using conventional concrete. You can use this kind of high performance fiber mixed concrete to increase its tensile behavior. Thus, we can increase our inelastic performance. Right now, I'm going to talk about a lecture topic: earthquake disaster and its mitigation, innovation in building design. So, what are the various earthquake disasters happened in India, and how it affects our buildings, and what are the codal procedures we do have in our India to resist such kind of disasters, and how to make your structure earthquake resistant one. Like, so you are seeing this is the earth top surface. So in top surface you can see we have sea, land, huge hills, mountains, and deserts, and various geographical locations we are having in earth's top surface. Likewise, our interior part of the earth do have different layers. You can see in this picture we have 4 different layers. The innermost red color part is known as inner core. It is in solid form. The next one is outer core. It is in a liquid form. And the third one is mantle. The mantle is subdivided into 2 categories. One is mantle, another one is upper mantle. And the last part is crust, where we are living. So here the important role is crust and upper mantle. The reason is while the joining place of this crust and this upper mantle creates a thin layer called as tectonic plates. These tectonic plates are playing major role in creating earthquakes. The reason is these tectonic plates are not a continuous plate. This is a rocky kind of surface. It is a discontinuous, or I can say it's a broken plate. And these broken plates are moving, slowly keeps on moving continuously. So what will happen if it moves continuously? This possibility of sliding and this possibility of colliding and this possibility of bumping is possible huge in this tectonic plates movement. In 1960, before 1960, our scientists don't have any idea about tectonic plates. They thought the crust is completely a continuous nature. Whereas after 1960, they came to know that our earth crust is not a continuous plate, which means our tectonic plate is a broken plate, and it keeps on moving. So if the plate is keep on moving, so possibility for sliding and colliding is possible. In such kind of circumstance, earthquake is occurring. Especially the boundary of each and every broken plate is called as broken plate boundaries, where in this plate boundary we have lot of fault region, fault, F-A-U-L-T. The reason is fault is the rupture or a fracture in a continuous rock mass, where you are going to face earthquake. In that exact location, usually the earthquake will occur. In that location, earthquake will initiate and it will transfer to the earth crust.
So it occurs only in fault region.
Fault region is the weakest region, sir. This is the merging point. Yes, sir. This is the merging point. So when it collides or when it side post, exactly in this location, I will show the image. So it will be in this like a sliding portion. If it slides, no, it will start somewhere in this region. So fault region is nothing but this is the end of the boundary. In the boundary line, you can see a slope surface. If it collides, so the earthquake will start from the fault region. That is a mode. So you can see in this picture. So can I point? Okay.
Give us the cursor.
Oh, yeah, best. So you can see in this picture, this is the fault region. So this is the plate and this is the one plate and this is the plate boundary and it is the fault plane. Where usually this is the yellow line and here it is also yellow line, which means a continuous mass. It has been ruptured or fractured. Okay. So this exact plane is called as fault plane, where usually earthquake will occur. Okay. Now in this layer you can see this is the earth surface and this is the crust region. This is the crust region and this is our upper mantle. Exactly in this location our tectonic plates are there. So after 1960 they come to know that tectonic plates are broken plates and our earth has 6 major continental tectonic plates and 14 subcontinental sized tectonic plates. You can see these are the major 1, 2, 3rd Pacific, 4th Australian plate, another one is African and South American plate. These are the major 6 continental plates and we have 14 subcontinental sized plates. Our Indian plate is one of the subcontinental sized plate. Usually all these, as I said, all these plates are keep on moving. So in our Indian plate, according to our Indian plate is merging with Eurasian plate. You can see Eurasian plate is above the Indian plate. Our Indian plate is usually merging with Eurasian plate, exactly on the location of Himalayas. That's why Himalaya is the active seismic prone zone. Now you can see Earth's surface is not even, it is broken plate. If you talk about tectonic plates along with the Earth's surface, it seems to be like this. Now one interesting is in Earth, in our world, Japan is facing more earthquake than any other country. The reason is, come to our plate. Our Indian plate is merging with Eurasian plate. Now you can see in this picture, this is Bhuj, where Gujarat is there, and this is completely Himalayan belt. So we are merging with Eurasian plate, only one plate. We are merging with only with Eurasian plate. Let us come to this location. This is exactly Japan is there. Here Eurasian plate is there, Pacific plate is there, and Philippine plate is there. These 3 plates are colliding with each other. So what will happen if 2 plates are merging with each other? Earthquake will come. So suppose in this case Eurasian plate is merging with Pacific plate and Philippine plate. So all these 3 plates will always merging, colliding and sliding past. So the frequency of earthquake is very, very high in case of Japan. That's why they are facing huge earthquakes than any other part of the world. You can see this.
Same is the case with the Philippines.
Yeah. So now what is earthquake? Earthquake is nothing but a sudden release of energy, I can say in terms of technical words, or ground shaking, sudden ground shaking. Because of what? The rupture or when colliding, the 2 tectonic plates are colliding or it slide past, the amount of energy is released in terms of stored up energy is released in terms of seismic energy and it transmits to our Earth surface in terms of waves, that is called as seismic waves. I can say this is a plate, this one finger is plate, and this one finger is, just assume these 2 as a plate. Now I am applying a frictional force. So this is this plate and this plate. I am pushing this plate in this direction, I am pushing this plate in this direction. While I am slapping, you can feel some sound. This sound is nothing but earthquake. This is sudden release of energy. While I am giving frictional force between this finger is capable to give such a sound energy, that is called as sound energy, and it is reaching me through air in terms of sound waves. Same thing is happening in our earthquake. When 2 plates are frictionally collides or slide past, what will happen? One plate will be under stress state, another plate will be in giving stress to that particular state. So what will happen is that after passing that plate, the stored energy immediately will release. In that circumstance, the energy in terms of waves is transferred to the earth crust. That waves is called as seismic waves. And in this picture you can see where exactly earthquake starts. That point is called as focus. or I can say it is hypocentered. Where exactly the earthquake reaches the top surface, it's a straight part. Where it reaches the top surface, it called as epicenter. Okay. Now a small video we're going to see about plate tectonics and how earthquake is affecting us. So sound increase.
They can collide with each other. They can slide past each other. Or they can move away from each other. Scientists believe that these movements of the Earth's plates bend and squeeze the rocks at the edges of the plates. Sometimes this bending and squeezing puts great stress on the rocks. Rocks being somewhat elastic in nature, they can bend without breaking. If the stress becomes too great, the rock layer will suddenly rupture and rebound to an unstrained condition. Whenever any of these motions take place suddenly, they release an incredible amount of 1960, scientists came to the conclusion that the Earth's rigid outer crust was not a single piece, but was broken up into about 6 large continental plates and about 14 subcontinental-sized plates. At the boundaries of the two plates, 3 kinds of motion can take place. They can collide with each other. They can slide past each other. Or they can move away from each other. Scientists believe that these movements of the Earth's plates bend and squeeze the rocks at the edges of the plates. Sometimes this bending and squeezing puts great stress on the rocks. Rocks being somewhat elastic in nature, they can bend without breaking. If the stress becomes too great, the rock layer will suddenly rupture and rebound to an unstrained condition. Whenever any of these motions take place suddenly, they release an incredible amount of energy. This causes the sudden shaking of the Earth that we all call an earthquake. Almost 90% of earthquakes are produced at plate boundaries. On this basis, we can identify 3 major seismic belts. One in the Circum-Pacific Belt, which encircles the Pacific Ocean, including the west coasts of North America and South America, Japan, and the Philippines. Another is the Alpine Himalayan Belt, which slices through Europe and Asia. And the third one is the Mid-Oceanic Ridge. The Indian subcontinent shows that the Himalayan Belt is one of the seismically active regions where several large earthquakes have occurred. 1960.
Let's come to the presentation. Now, as the video said, that the earthquake is transmitting through waves, right? Our seismic waves is classified into two categories. One is body waves, another one is surface waves. The body wave is the first wave, and surface wave is the followed by the surface wave. And body wave can be divided into two. One is P wave, another one is S wave. And surface waves can be divided into two. One is Love waves, another one is Rayleigh wave. P wave is the first preliminary wave. It is faster than any other wave. So when earthquake starts, is the first wave will reach the seismological laboratory to observe something is happening. The next wave is S wave, that is secondary wave or otherwise surface wave. The movement of P waves will be in this direction, only in a straight path with push and pull. With push and pull, you can see in this picture the direction of movement is only in a straight path with push and pull. Yeah, horizontal with push and pull, with push and pull. So it will cause some distraction, and this is very faster and can be able to travel on solid rock and on through the liquid in the liquid surface also. Let us come to next is S wave. S wave is the secondary wave or otherwise called as surface wave. Why we are calling that as surface wave? The traveling path of P wave is completely straight line, whereas the traveling path of S wave is completely like this. Okay, sinusoidal. So that's why we are calling that as seismic wave. Shear wave, and this will create a huge destruction to our landmass. But it can't pass through a liquid mass. It can only pass through a solid rock. Okay, and it is bit slower than the primary waves. That is P wave. Another one is Love wave. Why we are calling that as Love wave? In 1911, Mr. A.E.H. Love, who created a mathematical model to predict that wave. That's why we are calling that as Love wave. Love wave and Rayleigh waves are not faster like body waves. It can only travel in the surface of the earth, like in the crust region, not like our P waves and S waves. And this wave, the traveling path of Love wave is not in this sinusoidal, it is in this way. Okay, this is in horizontal sinusoidal, not in the vertical sinusoidal. It's a horizontal sinusoidal. Yeah. What means? Yeah. So what will happen? This will completely disturb your landmass, and it will disturb your buildings and structures, those who are in the earth region, its surface. Next one is Rayleigh waves. Rayleigh wave, actually this wave was predicted by Mr. Lord Rayleigh in 1885. That's why that wave is named as a Rayleigh wave. The direction path of Rayleigh wave is not like other thing. It is moving like this along with a rotation. It will rotate. It will squeeze your landmass. Thus, it occurs huge destruction to landmass. And Rayleigh wave is a very stronger wave than any other wave. P wave is faster wave, whereas Rayleigh wave is very stronger wave to destruct your structures. So this is how the waves are moving. So you just need to pull a spring and drop it. How it moves? It simulates the P wave nature. Just like in the second picture, if you drop a rope, it will move like this. It simulates the S wave. Like in this third picture, you can see the Love wave movements. Whereas in the fourth picture, you can see this along with rotation. So this is how the waves are traveling in our surface and creating destruction to our Earth surface. Now, how to measure these earthquakes? Earthquakes can be measured in two ways. One is under magnitude category, another one is intensity. So what is the difference between magnitude and intensity? So magnitude is measured in the term of a Richter scale, varies from 0 and more than 8. And if up to 4.9, it is categorized as a slight earthquake, and 5 to 6.9 it is moderate earthquake, and 7 to 7.9 is great earthquake, and more than 8 magnitude is very great earthquake. So what it means? Magnitude, the intensity, we should differentiate this. Like if I am slapping myself, I can feel some pain, but now I don't feel any pain because the applied force is very less. If I slap myself in a very hard way, I can feel some pain. So the applied force is measured in terms of magnitude, whereas the pain in my chin is measured in terms of intensity. Like so, according to the magnitude, if I hit me like this, I don't feel any pain, which means I'm not feeling my pain. So it is under slight category. If I slap a little faster, then I can feel some pain. It will become under moderate category. If I slap very huge, very high, then it will become under great and very great category. Now we are telling 5 Richter scale, 6 Richter scale, 7 Richter scale. So another phenomenon is 5 to 6. The difference is only 1 in terms of Richter scale, but it is not actually. The difference between 5 and 6 in terms of earthquake, if I can say, it is 30 times higher than 5. If you talk about 6 Richter scale magnitude, it is 30 times higher than the 5 Richter scale magnitude. Whereas come to 7, which means 30 multiplied by 30, which means 90 times higher than the 5 magnitudes earthquake. Okay. Now intensity. As I said, intensity is nothing but, magnitude is nothing but the recorded ground, according to the recorded ground motion data, we are measuring the earthquakes in terms of Richter scale, whereas intensity is the amount of destruction on the earth surface. Like I'm one example, in Chandigarh, if earthquake is coming, the magnitude is around 6. The some amount of vibration can be felt by Shimla people. So the magnitude remains same in Chandigarh as well as in Shimla, whereas intensity will differ. In Chandigarh, the damage will be huge, whereas in Simla, the damage will be very minor. Somewhat damage may not occur. In such cases, intensity may vary, but magnitude may not vary for an earthquake. And intensity is measured in terms of modified Mercalli scale, varies from 1 to 12, grade 1 to 12. So you can see grade 1 not felt by people, grade 2 felt by one person or by persons who are residing in the topmost floor. And likewise up to grade 1 2 3 there is no any severe thing, whereas beyond grade 4 to grade 12 we can see some kind of structural problems are there. In when you talk about grade 12, there's a total damage occurred in your building. So according to this, we need to grade your structures, and this can be measured in terms of intensity in the name of modified Mercalli scale number 1 2 1 2 3 up to 12. How these seismic waves are measured or can be plotted? Usually, earthquakes are recorded by instruments called seismographs. You can see in this picture, this is one of the very oldest type of seismograph. In this, you can see we have a spring and it is suspended with a weight. It's a ball, it's a weight with a weight, and there is a pen. This is a drum. This drum is keep on rotating slowly. It's a rotating drum. Okay, and now we are resting on weight with a pen. So the pen will hold on the drum. Okay, now the drum is rotating. If any earthquake occurs, that the weight will vibrate like this because it is suspended using a spring. So automatically the pendulum will move like this. So now we have a drum to rotate. So what will happen? The vibration can be measured in the drum in terms of seismograph. This is one of the world very old seismograph, and this is one of the new seismograph. Here we don't have any kind of weight. Okay, we have one needle like here. We have a needle that will measure the vibration. This is the rotating drum as usual. It will rotate and this will measure the vibration. You can see, and this is one of the seismograph. In earthquake engineering department, we have a seismic observatory laboratory, and it is below the earth ground surface. The reason usually this kind of laboratory will be in the underground surface to avoid the noise pollution, because these seismographs can measure any kind of vibration. If you walk, it will measure your vibration. If any truck cross, it will measure the vibration. So it is used to keep those kind of seismic laboratory beneath the earth surface. So in our department, we have a seismic observatory laboratory, and this is the exact seismograph what we are using in our laboratory. Now there is a small video how these seismographs are working. You can see in this video, the drum is not rotating actually in this video. So the drum is usually, it will be in rotating position. Now the needle will measure the graphs. So this is the exact seismograph. Okay, when earthquake starts, you can see the first wave is the P wave. The first wave, it's a faster wave to reach the seismological laboratory. The next wave is shear wave, followed by surface waves. This is how we need to differentiate the earthquake data. So from the past earthquakes, our Indian scientists who divided the Indian geographical location into 5 categories: 1, 2, 3, 4, 5. Previously zone 1 was there, but right now we don't have zone 1. So because earthquake may occur anywhere at any time, so we just remove the zone 1 category. Zone 2, 3, 4, 5, it is right with us. So you can see in this picture, green color denotes zone 4, whereas pink color denotes zone 5. Zone 5 is very, very great, and zone which means zone 4 is great earthquakes. We can possibility for great earthquakes. And actually all those regions are in the Himalayan mountain region. As I said in the earlier slide, it will possibly occur only where it merges, where the Eurasian plate, our Indian plate is merging. There the possibility of our zone 4 and zone 5 is there. So what are the earthquake effects? Usually if earthquake comes, landslide will come, surface faulting, tsunamis, liquefaction, and flash floods. So what are these things? So this is a landslide. For first figure is denotes a landslide, and second one is surface faulting. Faulting is nothing but a rupture or fracture in a continuous mass, as I said. So here the road surface is a continuous surface. Now it has been completely fractured. This is surface faulting, and this is flash flood, and this is tsunami. So all these three figures shows the problems associated with the surface, Earth's surface. Whereas tsunami is not like this, because it is occurring below the Earth's surface, which means below the ocean level. Suppose if earthquake occurs below the ocean level, sea level, what will happen? See, here two plates are merging, and here is the fault plane. Here is the focus point of earthquake. Now, seismic energy is transmitting in terms of seismic waves. You can see in this picture. Now, what happened? The depth of the sea in the mid region is huge, is high. The depth is able to capable of to resist that much of seismic energy, and whereas in our seashore area the depth is very less as compared with our mid region. So what will happen? The seismic energy can transfer from depth, mid sea to seashore, whereas in this third figure you can see that depth of the mid region is very, very high, whereas the shore level is very, very less. In this case, what will happen? The seismic energy will immediately dissipate in terms of giant tidal waves. That's why we are facing very high tidal waves during tsunamis and the shore level. So these are the various building codes and other safety codes associated with the earthquake resistant measures, which was released by Bureau of Indian Standard. Our Bureau of Indian Standard has many codal procedures, not only for buildings, for all kind of other works like mechanical and electrical, for all kind of works. And this IS denotes Indian Standard, whereas 1893 denotes the standard code number. So apart from this 1893, we will use to mention the year of publication, year of reaffirmation. Likewise, we have a lot of codal procedure. Our IES Indian Standard Code number 1 is the codal procedure for our Indian flag. It's not related to this, but I would like to tell you. IS code number 1 stands for codal procedure for our Indian flag. So generally we have two structure in civil engineering, that is load bearing structure, another one is RCC frame structure. What is the difference between these two? Usually in a load bearing structure, all the loads are bearing by a wall and transferred to the foundation. Whereas in framed structure, all the loads are bearing by beam and transferred to column through beam column joint, and finally all the forces transferred through column to the foundation. This is the principle, and this is the difference between this load bearing structure and framed structure. Because the phenomena of the performance and the response of framed structure is differ with our masonry structure. So likewise, the destruction, if anything happens because of earthquake, the destruction happens to masonry is different than the RCC frame structure. You can see in RCC frame structure nowadays we are constructing without infill and with infill, which means we can see in this third picture, this frame structure is partly filled with our masonry, which means that is infilled frame. Whereas in this case, in the second picture, you can see without, there is no any infill. So the performance and the response of these two frames will differ according to the infill. Now earthquake resistant measures at planning stage. So not only during construction, before starting your construction of your any building like load bearing structure or a framed structure, or it may be random rubble masonry structure, we should do some kind of planning stage by stage planning. Number 1. So we should construct our home little far away from the sliding slopes. You can see in this first picture, because earthquake occurs in this circumstance, immediately land will slide, so it will affect your home. Next one, our home should be construct, or our home should rest on a firm soil, not on the infilled soil. The reason is in filled up soil, the compaction may not be a proper, and voids possibility for voids is huge than the firm soil, because if voids is there, immediately during any shaking, that filled up soil can collapse or can distorted from its position. So immediately building will settle down. That's the reason we should not construct a home in the filled up soil. So if in such situation, we need to construct some homes in a filled up soil. What should we do? Yeah, we should go for a raft foundation along with pile foundation in such circumstance, because and this pile will take care about the sliding problem, and this raft foundation will take care about the settlement problem, uneven settlement problems. Usually this raft will integrate all foundations in our structure, thus it can avoid the uneven settlement of a building. Now plan of the building. If you want to construct a building with apart from a rectangular shape like T shape, L shape, we should have a proper segment gap between these two buildings, because during earthquake, according to your shape of the building will behave. If it is a lengthier portion and you are going to shake the earth like this, the performance is here, which means this building will perform better than this much length building. It is very it will collapse immediately if earthquake occurs in this direction, rather than like this. For a small example, you keep a cycle like this and just give a small push, it will fall down. Keep a cycle like this and try to give, no, it won't fall. That's the difference between a building in this direction and building in this direction. So earthquake may occur in any direction. It may occur in this direction or it may occur in this direction. According to the direction, your building will perform. So in this kind of plan, if you have a plan like this, it should have a proper separation joint, so that these two segments will behave two different behavior. Like in this case, you can see this L-shaped building is constructed monolithically, whereas in the next one is constructed with a separation joint. Same kind of forces we are applying in this case. This separation joint building is behaving differently, whereas the monolithical building behaves differently. Yeah, this is the first one is monolithic one, and the second one is separated one. If a failure occurs in a weaker zone, it will transfer to the stronger zone, so it will affect complete building. That's why we should provide a separation joint. Next one, and shape of the building. No, just a small example. That's right.
You have to take
Exactly.
water.
So okay, sir. And this is a water can. You can say, just we can compare this water can with the picture. Now I have a water can. I am applying a force. It just simply comes to its original position. The reason is the base is higher, the width is very higher than the top. Now I am keeping my building like this. What will happen if I drop it? It will fail immediately. Same thing will happen in these cases. So that we should not construct a building like this inverted pendulum type. We should construct a stable building. The third picture you can see, a building should be like this. It should not be like this. Now same thing, as I told you in the plan irregularity. So if you want to construct a vertical irregular building, you should have a separation joint, because pounding effect is more possible during earthquakes. During earthquake, if this small building gets shakes, it will deflect from its original position. This deflection should not affect the adjacent building. If you have a separation joint, it will not affect. If you don't have, it will directly affect on the next adjacent building. Third one, during earthquake, these projections, extra external projections will fall down immediately. Like what are the external projections we are using generally? We are using a cantilever and parapet wall. Parapet wall, that wall is called as unsupported wall. There is no any reinforcement for that wall. So during earthquake, during any kind of vibration, that wall will fall down immediately, and like this cantilever also will fall down immediately. So these are the projections should react immediately during earthquakes than the other kind of structural element. So it should be avoided in earthquake prone zone. And also, as I said, this water can example, same thing is happening here. It should not be like this. And this is called as floating columns. If you want to rise a column, you should rise from the foundation level. It should not be from the intermediate level, because that will affect the entire structure rather than the individual. I told you that we should maintain proper gap between these two, otherwise ponding effect will come. So what is the minimum criteria according to our codal procedure? This is the codal procedure. We need to maintain between these two buildings. Now, liquefiable soil. What is liquefiable soil? The soil which has more pores. During earthquake, what will happen? Not only the earth will shake. Because of this, the groundwater table will move from this place to this place, this place to this place. It will try to come up. During this time, our liquefiable soil has a lot of pores generally. So this water table will rise and come through the pores which is present in the soil. That soil, what will happen? If the pores are filled with water, so it will immediately settle. That will directly affect your building. So in those circumstances, we should go for a raft foundation or pile foundation. This is the actual phenomenon. Next, come to our masonry structure. Usually a masonry structure is a kind of box kind of structure. In this picture you can see is a box kind of structure. Whereas this wall is supported by the long wall. This long wall is supported by a short wall. Whereas in this case you can see this triangle portion is known as gable end wall. This is not supported by any kind of supporting walls. So what happens when the ground shakes? Immediately the gable end wall will fall on you, because we are residing inside the house. And next one is pitched roof. Rather than going for pitched roof and gable end wall, we should go for hipped roof. If you are going to construct a home with pitched roof, it should be properly braced. A pitched roof is like this. It should be properly braced. We are bracing in this only in this term. It should be properly braced in all direction like this. Okay, this is the gable end, and it is the bracings we are additional providing, and this is the another bracing, and this is the vertical bracing, and these are the tie members. These bracings, the bottommost bracings should be properly tied with our wall surface. Then only we can avoid the uplifting failure during earthquakes or during any cyclone also. So this is, I said, parapet is unsupported wall. So during construction, it should be properly anchored or properly connected with our structure. Through what means? Like this we can do. This is iron board we are using with a coping that will create a bond, that will create an anchor between the existing structure. Thus you can avoid a sudden failure of parapet wall as compared with the unsupported, which means without a strengthened wall. The height of the parapet wall should be as much as possible. We need to keep the parapet wall in a very small height, because more height it will fall quicker. Same thing, we should not keep some additional large huge mosses on the buildings top surface, because the top surface of the building will undergo huge deflection. Like this is my building, and when the earthquake occurs, the deflection in the bottom range is very less, whereas the deflection in the top portion is very huge. And thus during that time my building will vibrate like this. So that time what will happen, if you have a large water tank or swimming pool on the top surface, so it will, like, it will collide immediately. Thus it will reflect on our, it will give some impact load also. Just we have a huge water tank and it will falls on the surface of the roof level. So what will happen, that will create some impact load along with our earthquake load. So it will disturb our structure, and it just enhance the destruction level of a structure rather than saving our structure. So then now come to earthquake resistant measures in our masonry buildings. So what are the earthquake resistant measures we should do during construction? Probably we should avoid a long wall construction. Right, if you require a long wall, it should be properly supported by using a buttress. This is a buttress wall. Or otherwise, if your wall is crossing more than 5 meters, so then we need to provide a cross wall like we have done here. So this cross wall will hold this wall and will create a separation joint between the long wall. Thus we can save our building is the first step. Next, like it may be in masonry or it may be in random rubble. Like we are constructing like this in random rubble masonry construction. What will happen? We are keeping one stone here, we are keeping one stone here. We are filling this gap by using any mortar or any earth. During earthquake or any kind of immediate vibration, it will split. Thus, it will affect your entire performance of a building. So what should we do? We should have a through stone like this. If you have a through stone between these two layers, this through stone hold these two layers with the integrate way. So if this through stone can hold these two layer, so it can perform better during any kind of earthquakes. Likewise, in the corner, if you construct this wall, it will fall down, It should be properly anchored so that this weaker zone, this stronger zone can act uniquely and perform better. That's why we should go for a longer stone at wall junction like this. And in masonry construction, we should go for earthquake band. Earthquake band. What is earthquake band? So in each and every stage of the building, we have 4 stages, one at plinth level, another one at sill level, another one at lintel level, another one at roof level. These are the 4 levels in masonry structure. During plinth level, we should go for a band. During sill level, we should go for a band. In this case, you can see this is the plinth band. What is band? It will become in the next slide. And this is the sill level, and this is the lintel level, and this is the roof level. And we have openings. We should avoid large opening in our masonry structure. We should go for a small opening in our masonry structure, because larger opening will increase your weaker strength than the stronger portion. And also, along with the earthquake bands, we should go for a vertical reinforcement in our masonry structure. Vertical reinforcement, where should we provide? At the corner location. You can see this is the corner location. At the corner location, we should go for a vertical reinforcement. Wherever we are having opening in our masonry structure, there we need to provide one vertical reinforcement. Vertical reinforcement is nothing but a single reinforcement, okay, in every joint, in every openings. So this is the earthquake band. You can make this earthquake band using reinforcement, or using timber, or using cane wood, or any kind of band you should provide. So the reason for vertical reinforcement, the band will be held by the vertical reinforcement. So the entire building will act intricately to resist the earthquakes. So this is the masonry structure. During masonry structure, we need to go for a band along with the reinforcement. So this is a reinforced band. Previously, I saw that timber band. This is reinforced band. This is made up of our normal concrete, and when we are using our reinforced band, and over that should be filled with our again concrete. Then we can raise our masonry wall structures. This should be in the T joint. It should be like this in the corner joints. In our we have done a study how that earthquake bands are resisting the earthquakes and how it safeguard your buildings. Okay, and this building is constructed with earthquake bands and is tested under shock table, not under any shake table. It is shock table, which means I am giving a simple shock and how it reacts. That we can simulate with the earthquakes.
Earthquake bands must be provided to make a masonry construction earthquake resistant. These bands are nothing but a reinforced concrete member running over all the load-bearing walls of a building. Earthquake bands can be at roof, lintel, and plinth level. These bands integrate all the walls and avoid separation. Vertical reinforcement at the corners and junction of walls is also provided. This can be well understood with a shock table demonstration by earthquake engineering experts.
Well, under the huge shock, how this building has performed, which has earthquake bands, earthquake resistant elements, it has damaged but not collapsed. The same type of building, if these provisions were not there, then the building would have collapsed. Exactly this has happened during Uttarkashi earthquake, Ladu earthquake, Kilari earthquake, and the Bhuj earthquake. All buildings which did not have this type of provisions collapsed, along with them the inmates and the property had perished. So it is advisable to provide these bands. This has come into the Indian Standard Code of Practice. This provision has come and it can be used.
For brick or stone masonry, timber bands with mud mortar can also be provided, which can provide high strength at low cost. In the case of pitched roofs, gable ends are subjected to high earthquake forces. Gable bands can be used to protect gable ends. Alternatively, hipped roof should be provided. Long walls of more than 5,000 millimeters should be avoided. For such lengths, a reinforcement must be provided in the middle, or it should be joined by a cross wall in the middle. To avoid splitting in rubble masonry walls at joints, through stones should be provided in sufficient number. Openings like windows, doors, and ventilators weaken the walls. Therefore, the size of the openings must be small as far as possible, and they should be provided away from the corners and from each other. To compensate the loss of strength due to openings, reinforcement should be provided around the openings. If a pitched roof is required, the two slanted roofs should be joined through what are called bracing members. Projecting parts and attachments, such as balconies, parapets, suspended ceilings, and the like, should be avoided as far as possible, as these are the parts to get damaged and fall first. If provided, these should be secured to the main structure of the building using proper reinforcement. The height of the parapet should be small, and it should be properly secured to the building.
So these are the typical patterns of damage in masonry structures we have observed during our earthquakes in India. So cracking at separation joints, open out of plane wall collapse, and a total collapse, and crushing of other walls. So how masonry structure is behaving during earthquakes? As I told you, a longer wall can resist the more load than the shorter wall. Which means in this direction. According to direction, the performance may differ. So in this picture, you can see while pushing this building, this wall will react like this, whereas this wall will fall down. So in order to avoid such a circumstance, we should provide a proper connection in the corner joints. Thus, we can make the weaker section along with stronger section to resist such a earthquake forces. So this is the first figure. You can see this longer section is performing better than the shorter section, which means that span in this x direction. So it can be tied with the longer wall and this shorter wall, and can be connected with in the corner region. We can resist the earthquakes. And also we should avoid as much as possible the unsupported walls. If the wall, if you have a wall up to h height, you should not cross any level beyond the h height. In this figure, you can see it's a long wall and having the unsupported wall. So this kind of unsupported wall should be avoided. And in masonry structure, the more higher, this is not a safer one. So it should be shorter and it should be broader, because it is masonry structure, it is unreinforced. So to avoid such a overturning failure, it should have a short height with a very little higher width, so that we can avoid such kind of overturning failures. Generally, in earthquake resistant, especially in masonry structure, we are trying to create a box action. An effective box can resist the earthquakes better than any other shape. So we are trying to create a very good box action by creating all kind of bands and vertical reinforcement. Whatever we are providing, we are going to create a box action. We are going to make the building into a very better box than any other shapes, so that these kind of boxes will behave better in during earthquakes than any other shape, like triangle, you can say, any kind of shapes. But these boxes will perform better. That's why we are trying to create box action in earthquake resistance of masonry structures. And also we should avoid large openings. You can see in this picture they have large openings. These kind of large openings, what will happen? During earthquakes, immediately these kind of large openings will fail, which means the entire wall will fail. Thus that entire masonry structure collapse immediately during earthquakes. So as far as possible, we need to avoid large openings. We need to go for a small openings. So if you want to construct a small opening, it should be properly reinforced with earthquake bands. Now, in case of masonry structure, we are constructing a staircase like this. Just you can see in this particular region, we are inserting the slab portion, staircase slab portion inside the wall. This wall is unreinforced wall. During earthquake, what will happen? The top portion will split up, the bottom portion will split up. So the entire staircase will get collapsed. So if you want to construct a staircase, you should go for reinforced concrete along with the separation joint. Proper gap is required because masonry structure may behave differently, the RCC structure may behave differently. So in order to address these issues, we should have a proper gap between these kind of tools. And as I told you, we need to go for a proper band. Already I have explained you. These are various failures. So what is the role of vertical reinforcement in earthquake resistant measures in the masonry structure? You can see in this, when I apply a lateral load in the first figure, in the second figure, the entire building gets twisted, which means turning, overturning. The third figure, a lot of shear cracks is occurring, and finally the building will collapse. So what should we do? We should provide vertical reinforcement along with the earthquake bands. The earthquake band will integrate all the walls, whereas the reinforcement will hold the earthquake bands effectively, like this. While applying lateral load, rather than going for overturning as well as the shear failure, shear cracks in the structure, the masonry structure will behave like this if you provide vertical reinforcement. So vertical reinforcement is essential in case of masonry structures, every corner as well as in the openings. Because when masonry structure is subjected to earthquake force, immediately cracks will start in the corner of the, in the first picture you can see in the corner of the opening, the cracks starting and it keeps on widening. Whereas if you provide a lintel band and this lintel band is properly connected with vertical reinforcement, we can avoid such kind of circumstance in masonry structures. This is a splitting failure in random double masonry. So in random double masonry, if you want to construct, you should go for a through stone because that will hold these two layers. These are the various layers. Okay, now I have a building, I have a masonry structure which is not constructed using these kind of earthquake resistant measures. And how to increase its earthquake resistant measures? By using some strengthening method, I should increase the earthquake resistant measure of the building. How to increase such? You can see if it is in a masonry or it may be in a random double masonry construction, we should create a hole in the walls in various locations. And we should create a hole and it should be properly reinforced with the hooked bar as it shows in the first figure. And the rest of the portion will be filled with the concrete. What will happen now? If you reinforce this, if you place in this hooked bar with concrete, this will act as a through stone. This will hold the two layers. Okay, first step. Next step, wherever the opening is there, wherever the corner connection is there, we need to provide vertical reinforcement. But those kind of reinforcement is not possible in the existing building. So what should we do? We should remove the plasters in the corner region as well as in the opening, near openings, like doors and windows and the lintel levels. And we should go for a wire mesh. We should use wire mesh and we should nail the wire mesh on the wall surface. Now we should have a proper spacing between the wire mesh and the wall surface. Okay. Now then after this, we can use our concreting methods by manually or by using shotcreting to complete the final work. So this is the last figure you can see. They are completing the mortar work, and this is how your building will look after strengthening. So a strengthening building will behave better or not? That's the question. Is answering by our department experts in this video.
Cement or epoxy grouting. In the case of stone walls, stitch the walls with through stones or steel bars. Attach wire mesh to the face of the wall and cover plaster. To understand this better, let's go to Radhanpur in Gujarat. Here, people from nearby villages and towns are gathered.
Actually, after Bhuj earthquake, our earthquake expert just strengthened the buildings, and in order to demonstrate these strengthening measures, they constructed two model buildings in a same configuration without any strengthening measures, And one building is traditional way, another one building is after construction they have strengthened using our strengthening techniques, and they have tested in front of the people of Gujarat. Okay, so that they can understand the exact earthquake resistant measures in order to avoid such kind of collapse failures. Here also we are going for a shock type of loading rather than the shake table loading, because in practice shake table is may not possible, so that we are applying shock table by using tractor. You can see
cement or epoxy grouting. In the case of stone walls, stitch the walls with through stones or steel bars. Attach wire mesh to the face of the wall and cover with plaster. To understand this better, let's go to Radhanpur in Gujarat. Here, people from nearby villages and towns are gathered to see how stone or rubble masonry construction can be retrofitted.
This particular specimen here is as traditionally built. So the traditional masons and carpenters were employed to construct this. Exactly similar was constructed the other one. After doing the construction similar like this, that was retrofitted by applying certain elements. This is the condition. This particular specimen on the point of total collapse, whereas the strengthened one is still standing. This is a very interesting phenomenon that always happens in stone masonry. There are two layers of stones, one inside, one outside. At the time of shaking, the two tend to separate out and one of the layers tend to fall out. Now this is the weakness that must be safeguarded against. What do we do that? As you see here, these header elements, they were incorporated after the model was constructed. How they were constructed? A hole was made through and a steel rod was placed inside and concrete.
So this is way we can save our building from earthquake by using strengthening measures. Okay, now it is over for masonry structure. Yes, yes. Yeah.
How deep it is?
Deep is nothing but up to the wall width. Up to the wall width. Next topic is earthquake resistance measures for RCC framed structure. The behavior of RCC framed structure is entirely different than the masonry structures. Okay, the phenomena is entirely different. So these are the some various failures during earthquake we have faced. You can see in this figure, the first figure, second figure, and third figure. These two, the top stories are still alive, whereas the bottom story is gone. Whereas in this case, the entire building is completely collapsed. This each and every layer is nothing but a floor, but now there is only column, so it has been completely prepacked in the ground surface. These first two figure shows the soft story failure. Okay, this figure you can see all these three buildings shows the soft story failure. Soft story is nothing but we used to construct a building with car park. The car park is considered as the soft story. And next, that is the first kind of failure things, and this is the second kind of failure things. So usually what they are doing, improper conformant in the first figure. So though with proper conformant, the second figure shows failure. All these three shows column failure. Now come to this question. In earthquake resistant measure for our framed structure should behave in a ductile way than the brittle way. So what is the difference between these two? So you can see this is the first figure. We are expecting a hinge mechanism like this in earthquake resistant design measures. Because during earthquake, this entire building should respond like this. This mechanism is called as ductile beam sway mechanism. So whereas in the figure I have shown you the soft story failure. If soft story is there, then failure will be occur like this. The third failure. It is not recommended because if the building faced soft story failure, displacement is very high. Because during earthquake, my building should deflect like this. It should not fail after having such a small displacement. My building should not fail. So my building should go for a large displacement to resist the earthquakes and to keep those kind of measures will give you some time to escape from your building to be in a safer to be in a safer zone. Okay, that's a main ultimate aim of all kind of earthquake resistant design measures. So if your building is not obeying the sway mechanism, in this graph you can see after reaching its yield point, immediately it will fail. Whereas if your building is obeying the sway mechanism, beyond yielding point, the displacement may be larger. So this is called as ductile sway mechanism. We are trying our level best to provide such a sway mechanism enable building to resist the earthquake forces. In RCC framed structure, beam is connected with the beam column through a beam and column joint. This joint is the most vulnerable region of a framed structure because during in a normal loading, in a normal stage without earthquake, beam forces is transmitting through joint through the column and also the column axial load. So a joint is taking care of axial load from column and tension and compression from beam. During earthquake, this joint is subjected to earthquake force also because our joint is going to transmit all the forces generated by the building, generated by the earthquake to the foundation through the column. So our joint is the most vulnerable portion. So it should capable to resist all the forces and it should be live. It should be alive during earthquake. It should not fail immediately during earthquake. So our ultimate aim in framed structure is to save our joint from failure by creating failure in the beam, so that we are creating a lot of earthquake resistant measure in that cases that will be discussed in later slide. In our building, we have three important joint, that is interior joint and exterior joint and corner joint. Corner joint is the topmost roof level and exterior joint is the exterior part of the building, whereas interior joint is the inside of the building. It will be in a plus shape, it will be in T shape, it will be in L shape. So this is the joint forces during earthquake. So our building will our joint will face compression in one side, tension in another side, and lateral force in top sides. These are the various joint failure. If your joint collapse, then the entire building will collapse immediately. How to construct an earthquake resistant structure? We have a Indian standard 1893. We should follow this codal procedure to calculate the loads, to calculate the earthquake loads along with our gravity loads. And 13920, now we can calculate the load according to the first codal procedure and you can design the building. But apart from earthquake resistant, in earthquake resistant, apart from design, we should detail the structure very proper way. Then only we can resist that much of forces from the earthquake. Three main things we need to follow in earthquake resistant design, which is anchorage of main reinforcement, which means we have a beam and we have a column. It is connected like this. So the beam reinforcement should anchor into the column section properly. That is anchorage. Number two, confinement. So in this joint is the most vulnerable portion. So we have to confine the joint as much as we can. Number three, shear strength of the joint. Shear strength of the joint should be more than the beam, so that the failure can be transferred to the beam. So some of the following for procedure we should follow in our RCC frame structure construction. That is, first one is diaphragm discontinuity. What is this? Slab. We are having a slab on the beam, over the beam. So during earthquake, all the earthquake forces will carried by the slab, and it will transmit the forces through beam to column and to foundation. So if you have intermediate discontinuity, the distribution of forces will get affected. Thus, it won't distribute the forces and it will completely affect your building performance during earthquake. Another thing is stiffness irregularity. If you want to construct a column at top level, you should start from the bottom level. Otherwise, the stiffness irregularity will come and it will completely collapse the entire building during earthquake. Likewise, in the second picture, it has been clearly defined. And intermediately, you should not have a story. You should not increase the story height. And if you want to keep a long span, you should go for some other method. For in those cases, we should go for a proper column reinforced column. Otherwise, this kind of see in these cases in ground story, the fourth figure, in ground story we have nearly 6 columns, whereas in other stories we have only 4 columns. In intermediately we have only beam. No, it won't resist that much of lateral forces. So if you want to construct a proper building, a column from foundation to top should be properly well connected. Next one is mass ratio. As I said, in this case, same thing is here. This bottom, if I construct a home like this, then top portion I have a huge mass, whereas in the bottom portion the mass is very less. So during earthquake, what will happen? So it will affect severe, immediately it will get affected. So mass ratio is very, very important in your building construction. We should not have unwanted mass in our top surface or any intermediate. If you want to construct such a building, you should consider those masses. It should be evenly distributed throughout the structure. Next, the main principle on earthquake resistant design of frame structure is nothing but strong column, weak beam concept. The reason is why. The column is going to integrate all the members, structural members like beam, slab, everything to the foundation. So my column is the foremost important element in my structure than any other element. So what I am expecting, while doing earthquake, my entire building should act like this. In those cases, if your building should perform like this, my column should be more stable than beam. So another important thing during earthquake, so if I apply a load, here you can see a beam should bend, a column should not bend. Okay, such a mechanism can be created by plastic hinging by allowing hinges in beam rather in column, so that our in maximum of the world we are preferring strong column, weak beam. In this first picture, you can see the column is more stronger than the beam, so the failure can be transferred immediately to the beam. So if you transfer the failure to beam, which means hinges in this location, this joint connection, you can see here. If it properly forms hinges in this region, the entire building will behave like this. If not, the entire building will collapse like this. Okay. So this is the exact explanation. If a soft story failure is occurring, so the displacement is very, very, very less in the first picture. The second picture, you can see the displacement is huge because a proper hinge formation has occurred in this building. Our joint is a vulnerable portion because all the forces and moments are transferring through the joint to the foundation. So it is the most vulnerable portion. So now we have designed our complete building according to 1893 standard by calculating all the gravity loads and earthquake loads. Now, how to detail the structure? Detailing is very, very important in our structure. The reason is, in our column or beam, there are two types of concrete design. We are using only one concrete, but core concrete and cover concrete. Cover concrete plays important role in durability aspect, whereas core concrete plays important role in ductility aspect. So our ultimate aim is to save the core concrete to resist such a huge force. So how to hold the concrete? Just to providing the stirrups. By confining the concrete by means of stirrups in the terms of lateral ties or stirrups or any kind of reinforcement, we need to confine the concrete to hold the concrete within the core effectively. And also anchorage. As I said, beam should be properly connected with the beam column and properly anchored. The bottom reinforcement should go down. The top reinforcement should go down. The bottom reinforcement should go up like this. But in actual practice, what we are doing in this picture, you can see there is no any anchorage. If any earthquake occurs, the anchorage will, if your beam don't have properly anchored in a column, immediately it will split. It will come out. If the beam comes out, the entire sway mechanism will fail, because in our case a hinge should form in the beam. So if a hinge is forming in the beam, particularly in the hinge location, in this location, the forces will be huge. Our beam element should have the capability to resist such much of forces. So if your beam is not anchored, then the entire beam will come out. So the entire sway mechanism will get collapsed. So it should be properly anchored. According to our 13920, we should properly anchor. The anchorage length is clearly defined LD plus 10 dB. 10 dB is nothing but diameter of the bar multiplied by 10 plus the LD. LD is nothing but the anchorage length. Now, apart from anchorage, all the columns should be properly confined. In this figure, you can see the up to LO. LO is not the nothing but the hinge length in the column. It's a very important region in the column. So these regions should be properly confined by using stirrups or ties. You can say in any words. So it should be properly confined. What is the length of the LO? Linear lateral dimension of the column section, or otherwise we need to go up to 450 mm maximum according to our codal procedure. If you confine properly, if you design your building properly, if you do the confinement properly, it can resist large amount of shear force. It will give you a time to get escape from your building. And also in this bottom picture, you can see not only in the column region, in the beam region also we have to confine the concrete like this. The spacing is clearly defined. The spacing should be up to hinge length. That is the hinge length. 2D is the hinge length. Up to hinge length, it should be properly confined with the stirrups and beam as well as in the column. Okay. The spacing is given in our 139 detailing, and we need to follow that. And also in the column, because as I said, hinges should not form on column. Hinges should form only on the beam, except the bottom of the column. In the bottom of the column, we need to allow the column to form hinges on the very most bottom. Then only the entire building will allow to rotate more. That's why that particular region should be properly confined to resist that much of force. So we need to go for proper confinement in the foundation level itself. Next, what we're doing in practice, we are not following this kind of procedures. The reason is it is a little difficult if you feel, but it is not actually difficult. It's like a laziness, I think. We need to do a proper anchorage of stirrups inside the core. The length of the particular anchorage should be 10 times the diameter of the bar we are using, or otherwise greater than or equal to 75 mm according to our procedure. But in this case, we are to come to the next picture where I am showing the arrow. In this case, we are using maximum of the construction or doing this practice is not advisable, because if you do the hook the 135-degree, it will go inside the concrete and it will hold with concrete. Okay, it will intact with concrete during earthquake force. If you do rather than 135-degree, if you do the hook work with the 95-degree inclination, what will happen? Immediately it will split up during earthquake. So during earthquake, our compression and our tension and our lateral force, these three forces will create huge forces in the joint region as well as in all element of our structure. So what will happen if you are not properly anchored? If you anchor like this, it will come immediately, it will split up. So the entire structure will get collapsed. So it should be properly hooked in with the proper inclination. And also, if you are using multiple reinforcement in column, like this is the width of the column is 300 mm. Now I need to use one more reinforcement in the mid region. You can see in this mid region. If you want to cross more than 300 mm, we should go for proper additional ties, proper additional intermediate ties. Okay, not only the whole ties, intermediately we need to go for ties. What will happen otherwise? See in this picture, this column is properly confined only in the outer region. In intermediate, there is no any ties. Come to this picture. This is well confined, but though it failed because there is no any intermediate ties. So this single confinement cannot able to hold such kind of forces. So that we need to go for intermediate ties. Intermediate ties will hold your entire reinforcement along with concrete during huge earthquake forces. So that we need to go for intermediate ties. In these cases, you can see the sliding failure occurred. This is shear failure in column. It should not be happen in our structure. A man is showing with the scale, which means nearly half a meter. Nearly the confinement has done with half a meter height. It should not be. It should be very closer confinement so that it can resist large lateral forces. So proper confinement in RC structure enhances the ductility, stiffness property, inelastic behavior, energy dissipation, damage tolerance capacity, load carrying capacity, and hysteresis damping coefficient. It's nothing but energy dissipation. We should follow our codal procedure to resist such kind of forces. Thank you. So one more thing. If you construct, now we have a constructed building. Now we need to increase its if you want to construct the build, if you want to change the building into an earthquake resistant building, we need to go for some external strengthening using many various things are there. So I'm going to just share only one experience. Like this is external confinement. Internal confinement can be made using any kind of stirrups during construction. But after construction, we can't increase the spacing inside the building, so that is not possible. So we need to go for external wrapping using any kind of FRP FRP sheets. There is fiber reinforced polymer sheets. It's available in market. It is available in various form like carbon fiber reinforced CFRP, glass fiber reinforced GFRP, basalt fiber BFRP, silica fiber SFRP is available. So the strength will vary according to the fiber nature. So these kind of remedial measures we can take to increase its earthquake resistant measures. But one thing, this kind of confinement won't provide a ductile mechanism, but it can increase the strength of the building so that you can resist the building up to a certain increased strength level. These are the various strengthening measures. If you are talking about a building, especially in the hinge location, if you want to increase the shear capacity, we need to go for a FRP wrapping like this. These are the various different configuration how to provide FRP wrapping. This is a reinforcement, and we need to go for a U-wrap. So before going to U-wrap, the corners in the beam should be properly curved. It should be made into curved shape. Then only it will, because otherwise, what will happen? We have a sharp edge. Now we are doing the wrapping. During stress concentration, what will happen? A sharp edge will completely destruct the FRP wrapping, because FRP is a flexible material. When we apply along with epoxy, it will become a brittle material. It is not a ductile material. So what will happen? It will act as a plastic like a plastic material. The sharp edges acts on the plastic material, it will completely rupture. So that the surface in the corner should be curved. So without FRP, you can see this first picture. Without FRP, that is, deflection is huge, whereas strength is very less. In the second picture, you can see the second layer. They are using a single layer of FRP, which means it increases the strength, but simultaneously it decreases the deflection property. In the second three layer, you can see the strength is very high, but the deflection is very less. So if you want to go for a FRP strengthening method, yeah, we need to go for a proper layer choosing according to the required strength. If my required strength, if my building is very weaker in strength, then I need to focus only on strength rather than deflection. If my strength is very high, I need to go for deflection. Then I need to go for small layers, then huge number of layers. How to wrap a column? This is how we need to wrap the column. So what will happen? So like during wrapping, now we have confined and now we are applying the axial load. So this confinement action will act towards this, towards the inner surface, towards the interior part of the concrete, so that it can increase the compressive strength. We can increase the strength of the column member through this kind of confinement. So this is the one bridge in Maryland. It has been constructed in the year 1969. Again, it was retrofitted, strengthened using this kind of techniques to increase its performance. So we can see various testing, various research is going on to increase the beam, because beam column joint is the vulnerable portion in the frame structure. So how to increase its performance? So in this way, many research work is going on in this sector to increase its performance using different wrapping techniques. You can see in this picture, a column is strengthened, whereas in another second picture, the beam is strengthened. So they are just to evaluate how these kind of wrappings are increasing its performance level. See in this picture, the unconfined one failed immediately. This is another thing. Whereas the wrapped one transferred the failure to next stage. This is a various way how to wrap a structure. This is the exact method during in our existing building, because laboratory studies may differ with our practical possibilities. So this is the exact way to wrap our existing building to increase its strength only in the beam column joint region. Thank you.